Welcome to the General Chemistry 2 class. This section is on chemical kinetics. This lesson is about the reaction's half-life. Let's begin. In this lesson, we will discuss the effect of reactant concentration on the half-time of a first-order reaction. Half-life is the time it takes for a reactant to reduce its concentration by half of the initial concentration. We can derive the equation for the half-life of a first-order reactions using the integrated rate law. Consider a first-order reaction whose integrated rate law is given by concentration of A equals initial concentration of A times E raised to the exponent negative kT. At T equals T1 over 2, the concentrations of A equals 1/2 the initial concentration of A. Simplifying gives us 1/2 equals E raised to the exponent negative kT 1 over 2. Taking the natural logarithm of both sides of the equations gives us in 1 over 2 equals in E raised to the exponent negative kT 1 over 2. Applying laws of logarithm, we obtain negative into equals negative kT 1 over 2. In solving for T1 over 2, we get T1 over 2 equals into over K. Notice that the half-life of a first-order reaction does not vary with the initial concentrations of the reactant. If we graph the half-life against the initial reactant concentration, a horizontal line is obtained. Example number 1. The decomposition of hydrogen peroxide is a first-order reaction. What is the half-life of the reaction at the rate constant is 7.30 times 10 raised to negative 4 inverse second. Solution. The problem asked for the half-life. Use the formula T1 over 2 equals N2 over K. Substitute the given value of the rate constant. The half-life is then equal to 950 seconds. Radiocarbon dating, or simply carbon dating, is a method of determining the age of an organism's remnants based on the amount of carbon negative 14 isotope remaining. At the death of an organism, the carbon negative 14 content is at 100%. As time goes by, the amount of the isotope decreases or decays. The decay of the isotopes obeys first-order kinetics. The half-life of carbon negative 14 is 5,730 years. This means the quantity of the isotope is reduced to 50% of the initial amount after 5,730 years, to 25% after another 5,730 years, and so on. Steps in age estimations by carbon negative dating. Carbon negative 14 dating rather. Calculate the rate constant from the half-life. The rate constant equals 5,730 years for carbon negative 14. After the rate constant is determined, the age can be calculated. Age equals negative 1 over K times the natural logarithm of the fractions of the isotope remaining. Example number 2. Estimate the age of a fossil if the amount of carbon -14 in the material is 32% of the original. Solution: calculate the rate constant. The rate constant equals 1.209 times 10 raised to -4 inverse year. Now, we can calculate the age given the rate constant and the fraction of carbon -14 remaining, which is equal to 0.32. Simplifying, we get 9.4 times 10 cube years. Let us look at the half-life of zero, negative, and first-order reactions. For zero-order reactions, consider the integrated rate law. Again, at the half-life, the initial concentration is half. Simplifying the equation, we get T1 over 2 equals initial concentrations of A over 2K. The half-life of zero-order reaction is directly proportional to the initial reactant concentration. Increasing the initial concentrations of the reactant takes longer time to reduce its concentration by 50% compared to reactions with lower initial reactant concentration. Graphing the half-life against the initial concentration for a zero-order reaction, a line with a positive slope is obtained. Now, consider the integrated rate law for a second-order reaction. Again, at the half-life, the initial concentration is half. Solving for the value of T1 over 2, we obtain T1 over 2 equals 1 over K times initial concentrations of A. The half-life of a second-order reaction is inversely proportional to the initial reactant concentration. A reactant of higher initial reactant concentration takes a shorter time to reduce its amount by 50% compared to a reactant of lower initial concentration. To summarize, half-life is the time required for a reactant to reduce its amount by 1 over 2 the initial concentration, or 1/2 the initial concentration. For first-order reaction, the half-life is not affected by initial reactant concentration. For zero-order reactions, the half-life is directly proportional to the initial reactant concentration. For second-order reactions, the half-life is inversely proportional to the initial reactant concentration. The decay of carbon -14 isotope obeys first-order kinetics and is useful in estimating age for remains of living organisms. And that's all. Thank you. Welcome to the General Chemistry 2 class. This quiz is about the reaction half-life. Let's begin. Select the correct answer. Question number 1. Which of the following statements is true about half-life? Number 2. What is the effect on the half-life of a first-order reaction if the initial reactant concentration is doubled? 3. What is the effect on the half-life of a zero-order reaction if the initial reactant concentration is doubled? 4. What is the effect on the half-life of a first-order reaction if the initial reactant concentration is changed from 0.02 moles per liter to 0.005 moles per liter? 5. Which of the following plots is corresponding to a first-order reaction? Sixth, which of the following plots is corresponding to a second-order reaction? 7. What is the half-life of a first-order reaction with initial reactant concentration equals 0.50 moles per liter if the rate constant is 0.671 inverse second? 8. What is the half-life of a first-order reaction with initial A concentration equals 0.100 moles per liter if the rate constant is 0.00437 inverse minute? 9. What fraction of a carbon-14 remains in an 11,460 years old bone? 10. The remaining carbon-14 isotope in a specimen from a mummy was found to be 74% of the original quantity. How old is the mummy? The half-life of carbon-14 is 5,730 years rather.